Hi, I am Varun Joshi and welcome to day 25 of our Certified Kubernetes Administrator 2025 course. It feels great that me and you have come so far. We are on day 25. Over the past few sessions, we have had some deep dive, longer lectures covering critical Kubernetes concepts. So today, I want to keep things a little bit lightweight and digestible while still covering an essential topic, Kubernetes core and extended architecture. Now, before I talk about this slide, I would want to visit day 8 again. We learned that Kubernetes was originally created by Google, and in 2014, Google released Kubernetes as an open source project. In 2015 itself, it came under CNCF, and CNCF in itself was founded by Google. However, now CNCF is independent body that works under the Linux Foundation. There are multiple key projects that are hosted by CNCF. Being a DevOps engineer, you would be working on these tools: Kubernetes, Prometheus, Istio, Envoy, etcd. etcd is the DB that we use in the control plane of our Kubernetes deployment. And then we have Helm. Helm we'll also see later in this course. Core DNS is the DNS that we have been using in Kubernetes, and there are many more projects. So let's come back to today, that is day 25. This line says that Kubernetes follows a highly modular design. Instead of embedding all functionalities into the core, it relies on plugins, add-ons, and third-party integrations to extend its capabilities. Let's break this definition. Firstly, since the inception of this course, we are talking about decoupling. If you remember, we started with a monolithic application. We decoupled that into 3 different categories: the front end, the back end, and the database. Then we further evolved that design into a microservices architecture. And in microservices architecture, we divided the application into different microservices, and these microservices are independent of each other. For example, if my wishlist microservice is down, then my orders and payments and rest of the microservices pertaining to that application will continue to work fine. And by decoupling these things, we ensured that not the entire application is down at once. That was our use case for using microservices. Each microservice served a specific purpose. For example, if you have the wishlist microservice, then wishlist microservice just held the logic of how the wish listing would work. How can people add products in the wish list, how they can remove, and so on. So the application code per se was only concerned about wish list, nothing else. Similarly, if you come to the text that you see on screen, Kubernetes has a core purpose. And what is the core purpose of Kubernetes? The core purpose is container orchestration. Kubernetes does not care how a container or a pod is created. Kubernetes does not care about the underlying networking. Then what is the core purpose? The core purpose is container orchestration, and that is the reason. So Kubernetes has said, my core is ensuring the container orchestration works. Rest anything else, I have outsourced to different companies, to different vendors. However, what Kubernetes has done is it has created some standards. So for anything that I have outsourced, there are certain standards that you must adhere to. And as long as you adhere to those standards, you are good to use your own system. My core will remain same, but anything else can be added. So let's zoom in into this concept and understand what is part of Kubernetes core and what is not part of the Kubernetes core. The core is your control plane components and your node components. The control plane component is your API server, which acts as an entry point for intra or inter-cluster communication. There are many more utilities of API server, but we are just mentioning the critical ones in this lecture. If you want a deep dive into control plane, data plane, then I would recommend you go to day 7. That is where we have discussed the Kubernetes architecture in greater detail. We have also demonstrated how each component behaves when you create a deployment. So it's a good place to start. Then you have scheduler. Scheduler is responsible for scheduling workloads onto nodes. There is controller manager, which ensures the desired state of the cluster matches the current state of the cluster. etcd is the database. Then there is cloud controller manager, which ensures that your Kubernetes deployment can interact with the cloud provider's resources. For example, if you are on AWS, you can seamlessly communicate with secrets manager, KMS, application load balancers, and many more things. Then you have node components. In node you have Kubelet. Kubelet is responsible to ask the container runtime to create the containers, monitor the containers, and there are a lot more functionalities that Kubelet performs. Then there is Kube Proxy, which performs service to pod networking. So these things are Kubernetes core. So the developers, the Kubernetes community. What is the Kubernetes community? Kubernetes community is a group of passionate developers, DevOps engineers like you and me who are eager about technology. And not just people, the Kubernetes community also comprises of organizations like Google, AWS, Red Hat, Ericsson. They all have some contribution in the Kubernetes development. So these organizations and these people form the Kubernetes community. So the Kubernetes community is responsible to handle the Kubernetes core. If, let's say, deployment introduces a new feature, I'm talking about the Kubernetes deployment object. If there is a new feature introduced, it is the Kubernetes community that is responsible for that. They are making the development, they are testing those things. If there is an update in the controller manager, it is Kubernetes core who is working on that. So anything pertaining to these things is the responsibility of Kubernetes community and hence falls under Kubernetes core. Now, what is not part of Kubernetes core? First categorization is plugins. What is a CNI plugin? CNI plugin is associated with networking. Kubernetes core says, I don't care how one pod talks to another pod. That's not my core task. My core task is container orchestration to establish communication between pods irrespective of which node they are residing in. Use a CNI. Then there is CSI for storage. CRI is for container runtime. Then there are various add-ons like ingress controllers. So ingress controllers we'll see later in this course. They are responsible for distributing traffic in your Kubernetes cluster. They support something called host-based and path-based routing rules. We'll see them in detail later in this course. Then there are different monitoring tools. Monitoring tools could be tools like Neuralink, Prometheus, and there are many more third-party tools. Service meshes. Service meshes define how the microservices within your cluster will interact with each other. What will be the security of those things? So there are service meshes that you can use as add-ons. Then there are third-party extensions. As you progress in your Kubernetes learning, you will learn about all these things slowly and steadily. So don't hurry as of now. Just take these things as a high-level understanding, and when we progress with this course, there are a few things that you see on this screen we'll be zooming into. There is Helm and there is Prometheus, and there are many more things. So these things are not part of the Kubernetes core. In this particular lecture, we will be zooming into these plugins and how they play a role in ensuring your workloads run seamlessly. Let me scroll down. This is the Kubernetes core like we just discussed, and then these are plugins that extend the capabilities of your cluster, and how they extend these we'll see in detail. The first thing I want to discuss is CRI. CRI is Container Runtime Interface. If someone just says CRI, then CRI is essentially a set of standard or a set of rules that are defined by the Kubernetes community, and Kubernetes community works under the governing body CNCF. Hence, any company or any person or anything that adheres to the rules set under CRI can write their own container runtime. CRI essentially is an interface that defines a set of rules, a set of standards. The expanded form for CRI is Container Runtime Interface. Then there are different plugins for CRI. Plugins are something that are developed by developers and hence companies. The examples are CRI-O, Containerd, Podman, Kata containers. The responsibilities of a CRI plugin, of a container runtime plugin, are container lifecycle management, image management, logging, and security. These are not the only responsibilities. There are many more. These are just an example of the responsibilities that a CRI plugin performs. But Varun, help me understand one thing. Why didn't Kubernetes core include CRI in part of the core itself? Why is it separate? Because container runtime is just pulling the image and performing all things container related. But like I mentioned before, Kubernetes core is container orchestration, not creating your containers and ensuring security for them. This is not the core of Kubernetes. Core is container orchestration. And again, anyone who adheres to this CRI can write their own container runtime. You also see Containerd here, and Containerd in itself is developed by the Kubernetes community and is a CNCF project. Then why can't Containerd be the default container runtime, and why go to extents of having so many different runtimes? That is because each project, every application has its own requirements. You cannot have all of them use a single runtime. So I'll give you an example. So Containerd you will see is the default for most setups, and it is lightweight and optimized. Then there is CRI-O, which is also called CRI-O. CRI-O is designed for OpenShift and tightly integrates with Kubernetes. What is OpenShift? OpenShift is also a distribution of Kubernetes like Amazon EKS, Azure Kubernetes Service, and Google Kubernetes Engine. There is OpenShift, which is by Red Hat. OpenShift is also a distribution of Kubernetes, and OpenShift uses CRI-O. So any deployment that you will see of OpenShift will be using CRI-O. And then there is Kata containers. It offers hardware isolation for better security. So if your requirement is that, then you could use Kata containers as your CRI plugin, as your container runtime. Then there is gvisor. Gvisor is by Google, and it provides user space sandboxing for untrusted workloads. Now, do you have to know these things in detail? No, but I want you to have an overview of all these things. Then there is CNI. CNI is Container Network Interface. This thing sets a standard for the rules that anyone who is writing a CNI plugin must adhere to. Examples include Calico, AWS VPC CNI, Flannel, Cilium. The responsibilities of a container network interface plugins are pod networking, manage how pods can speak with each other, IP address management, routing and connectivity within your cluster, and security enforcement. How security enforcement? Later in this course, we'll look into network policies, which ensures only certain workloads can communicate with each other depending on your compliance and security needs. So why do we need a CNI plugin? Same question that we answered here. Why can't I have a standard CNI, only one CNI for everything? That comes down to requirement. If I talk about these cloud providers, the big three, Amazon, Google, and Microsoft, then they all have their network tooling. Now, not all network tooling is same. Hence, we need a different CNI plugin for each of the cloud provider. For example, AWS VPC CNI is used in Amazon EKS. Similarly, AKS will have Azure CNI plugin. But Varun, Kubernetes is open source, firstly. And secondly, EKS, AKS, or any cloud provider's managed service for Kubernetes is using vanilla Kubernetes. And then they are doing some extensions on top of that. So can't I use Calico or Cilium when I'm working with Amazon EKS? Is it a mandate to use AWS VPC CNI? No, you can use any CNI plugin that you want to use, even if you are on a cloud provider. But what happens is, when you are on Amazon and when you are running an EKS cluster, there are certain features provided by the VPC CNI plugin that are not available anywhere else. For example, pod security group, they are available with AWS VPC CNI, and as far as I remember, I don't think any other CNI plugin offers that. Hence, it is recommended that you use cloud native CNI plugin whenever you are on a cloud provider. Now, how it also helps is, when you are troubleshooting or when you are stuck somewhere, then you can use the native cloud providers support to solve your problems. Hence, that is a recommendation that you should go with the CNI plugin provided by the cloud provider itself. But why would you want to use something else? See, there are always corner cases. There are always specific use cases. Then why would you want to use Calico? Because Calico is ideal for environments that require advanced security and BGP routing. If your requirements are that, then you would be using Calico. And this is not only limited to cloud providers. Even on-premises deployments could be using these CNI plugins. And of course, with on-premises, you cannot use AWS VPC CNI or Azure CNI until and unless you are ready to do some tuning and tweaking. You would be using other CNIs. Then there is Cilium. This is ideal for high performance networking and security deployments. There is Flannel. Flannel is quite lightweight, but Flannel does not support network policies. Then there is ViewNet. ViewNet is used for encrypted communication between pods. So when you want that type of a security, you can choose ViewNet. Hence, there are multiple options, so that you as a consumer can choose the CRI or CNI based on your requirement. So why did I fit this topic here is because of CSI. Since in the next lecture we'll be discussing Kubernetes volumes, I thought it will be best if I introduce CSI before going to the Kubernetes volumes. So what is CSI? So if you remember, in the previous lecture, we discussed Docker storage is handled by two drivers. First is the storage drivers, and then there are volume drivers. Storage drivers are responsible for ephemeral storage. So anything that goes with the container lifecycle. So if a container dies, that data also dies. If you have any confusion pertaining to this concept, I would recommend you watch day 24, because there we discussed these things at stretch. And Kubernetes follows the same. If you create a pod and then you write some data in the container that is part of that pod, and then you terminate that pod, then your data is essentially gone. Because that data's writable layer, because that container's writable layer was ephemeral. So as soon as the pod died, the data went away with that. So the ephemeral data part is handled by storage drivers, and then there are volume drivers. So whenever you add a persistent disk to your pod, maybe because you want to retain some data. It could be your logs or your application data, or you are running stateful applications on your Kubernetes cluster, then you would be using volume drivers. Now volume drivers are there to persist data like we discussed. So whenever you will be adding an external disk to the container in Docker, you would be using volume drivers. Kubernetes follows something similar, but they have CSI to handle this. Why do we need container storage interface? You need container storage interface plugin to interact with the external storage. So CSI, like we discussed about CNI and CRI, this is container storage interface. These are the set of rules, set of standards written by Kubernetes community that a person must adhere to, and if those set rules and standards are adhered, that plugin can work with Kubernetes to assign external storage to your pods. Examples include AWS EBS CSI driver, Google's persistent disk CSI drivers. So there are many drivers that can help you connect with external storage. So for example, if you are on Amazon, you would need a CSI plugin which can help you interact with Elastic Block Store, which is the block storage in AWS. If you want to access their EFS, there are drivers for EFS. If you want to access persistent disk in GCP, then you would use GCPD CSI driver. Similarly, there are drivers for various storage vendors which you would be using to interact with that storage. For example, if you are running your cluster on ESXi hosts VMware now Broadcom, then what you would be doing is there would be a driver that can help your pods connect with the VMFS in your ESXi. So these are the drivers that enable that communication with external storage. So responsibilities of a CSI driver: volume lifecycle management, snapshot and cloning, expansion and resizing, dynamic volume provisioning. So rest of these are self-explanatory, but dynamic volume provisioning is whenever I create a pod that says I want 10 GB of storage, then that 10 GB of EBS volume, if you are on AWS, is created and assigned to your pod. So I hope you have a good understanding of why Kubernetes follows a modular architecture, why there are plugins, why there are add-ons, why there are third-party toolings. Now, there are some benefits of this modular and extensible architecture. I want to quickly discuss those benefits, and before I do that, I would recommend you also go to the GitHub notes day 25, and if I go to references, you can find that I have added all the references. You can go to these places and this will have the official documentation. So this is the official documentation for CNI. If you are interested, I would recommend you go through these references and have further understanding of these plugins. I'll go back here, and I think it would be better if I teach the benefits right from here. Yeah, why Kubernetes uses a plugin based architecture. So the first one is interoperability. You can use various plugins, third-party tooling without disturbing the Kubernetes core, and this provides you better interoperability. Then there is flexibility and vendor neutrality. You know that there are various vendors for CNI, CRI, and also for CSI. You can choose which one works best for you. Encourages innovation. Now, since each company or each organization has its own plugin, third-party tooling, etc., then they can work on enhancing that specific thing. For example, if I talk about CRI, Kata containers offer something that CRI does not offer. So it has an advantage where some customer is looking for highly secured container runtime. Then there is scalability and maintainability. Individual components can be scaled and upgraded independently, improving reliability and maintainability. So this is self-explanatory. I think that's all I wanted to cover. That's a wrap up for today's lightweight but crucial session on Kubernetes core and extended architecture. We covered how Kubernetes is structured and how its plugin based approach allows for powerful extensions and why this flexibility is key to its success. Up next, we'll dive into Kubernetes volumes, an essential concept for managing storage in Kubernetes cluster. So stay tuned. If you have any questions, feel free to ask them in the comments section and I will reply. If this helped, do consider liking, sharing, and subscribing. It will mean a lot to me. Thank you very much.